Hello everyone, welcome back to the channel, and today we're going to be looking at another USACO problem from the January contest bronze on astral superposition. Now, as I always say, I encourage you to go back, read the problem, maybe try to develop a solution, and if you don't understand it, I'll try to explain it as the best to my ability. So I'll give you a second to do that. Okay, so I hope you read the problem and tried to understand it, and if you didn't, well, I hope this explanation helps. So, first, when you try to read the problem, it says that we're looking at like a square in the picture of the sky, right? And each square is either empty or it has one star, and no two stars share a square. So what I can write here is we have an n by n grid, as it says in the problem, and in each cell it can be either empty or one star. So that's what we have currently, and it also says here that Bessie took 2 photos, and one before and one after. So we're also given that. When you're doing these kind of problems, it's always good to write all the information that you might need, because it does give the constraints as to like what you should do, but to understand the problem, this is a good strategy to always write everything that you need to know. And then it also says that overnight, every star does exactly one of these things. It disappears, or it moves a square right and B squares down. And you can see that over here. Right? It says right here, they'll move A squares to the right, B squares down. So we can go ahead and write the rules real quick. Star rules. It can either disappear or it can move A to the right or B down. So, and after that, it says if a star moves off the picture, it disappears. So if it moves out of the n by n grid, it will disappear, and no new stars will appear. So every star that we see must have started in photo 1. So now we kind of are starting to understand the problem rather than just reading what is on the problem. So there's no off the grid, that means it's gone, no new stars, and all stars start in photo 1. Right? And we also know that Bessie accidentally stacks the 2 photos on top of each other. So now we're getting to the problem part, like what she did wrong. So instead of 2 images, now we have 1 mixed image with photo 1 and photo 2. So we just say photo 1 plus photo 2 is new image. And each square in this final image has one of 3 colors: white, gray, or black. So we can just say WGB, or I'll just say white, and it has some conditions for each of these. So white means empty, right, in both photos. Gray just means the star is in exactly 1 photo, and the black means the star is in both photos. So now we get to the actual question. So we're given this final image, right? And our job now is to find the minimum, right? The minimum number of stars that could have existed at the beginning. So that's our goal, to find the minimum. And if there's no possible way to make this image using rules, we have to return -1. So now that we've gotten our explanation here, now let's think about how can we develop a solution. Well, one method is that we could just guess what the second photo looked like, and we just rebuild the first photo, but I feel like that would take too long. So instead, yeah, let's actually rebuild the first photo. And why? Because I feel like every star must like start there, right? And if we rebuild photo 1, every star must start there because that's where it begins, right? So every star must start there, right? Now we can just handle one color at a time. So each color will tell us different information, so we handle them one by one. So our order for this would just be black, white, and gray. So we start with our black squares, and a black square basically means that there's a star in both photos. There must be a star originally here, right? So we can write black would be a star existed before, in the before photo, right? Before photo 1. And because stars only move in one fixed way, there must also be the same star at the original position that it originally moved from. So B, when it's at R, C, the star must also be at R, C. And the star could also be at R minus B, C minus A. Because remember, it could either disappear or it could move A right and B down. Right? So you got to include that case as well. So now, if the earlier spot is outside the grid, then that means it's impossible, right? And when it's impossible, we have to return -1. Right? So just remember that. And white squares, which are forbidden, means that there's no star that existed in either photo. So we're not allowed to, put a star here. So we can include that, right? So white W, no star allowed. Okay? And if anything ever forces like a star, into like a white square, then the answer has to be impossible, right? We can just get that from our explanation. So a star on the white one would indicate that it's impossible, therefore you just return -1. So I'm just basically reiterating what I just said, but making it more easier to when we actually have to code it. Now, here's the one that's a little bit confusing. We have the gray, right? And gray is only flexible for one color, meaning it has exactly one photo, right? One photo had a star. So we can write gray G, the star is in one photo. And keep in mind that the number of stars is minimal. So we add a star if we absolutely have to, right? So we want to add as few as possible. Remember, that is our goal, minimum stars in photo 1. So for the gray, if it's already explained by a star moving here, we don't want to add another one. So we do that. Now, otherwise, we have to add one star, right? So we can just write our gray rule real quick. And if unexplained or not shown, then you can add a star. Now, here's the final step. So after processing all of this, we count how many stars are placed, and that's our minimum answer. So we just can say our answer is going to be the total number of stars placed, or the total number of stars there. So now let's go to Visual Studio Code and code this thing out. First, we want to do the include bits stdc++ H because this actually gives the program access to almost all the standard C++ tools, right? With things like using lists, using strings, etc. Then we want to do using namespace std, and this basically puts common tools inside something called an std, and this lets us write vector instead of having to write std : vector, or sin instead of std : sin. It just makes it easier to write it and more clear. Now we have to write our first function, which is int solve case, and what this means is that we're creating a machine called solve case, and this machine will basically solve one test case and return an integer number, the answer, or -1. So basically you can think of it as like giving me one problem and I'll give you an answer. Then we have to introduce our basic numbers, which is in n, a, b. N is the size of the grid, a is how far right it goes, b is how far this down it goes. So this is related to the stars. Then we have to do sin. We have to add the sin part, and this computer will read the three numbers from input, and it'll basically store them into n, a, and b. So now we can store our positions and grid numbers. So and then we have to read the final image, so we have to use a vector string final image, and this will create a list with n rows, and each row is a string of letters, and each letter could be W, G, or B, and this will store the final photo. Then what we have to do is we have to add a for loop, and this will run n amount of times. Each time it reads one row of the image, and then it'll save it into the final image. After this, the final image will tell us the color of that pixel. So then we have to create the star tracking grid. And this is a little complex, but we basically are just creating an n by n grid. In each spot here will hold a true, which means a star must have existed originally, or a false, which basically means that no star is placed yet. So you can see there's a boolean here with false, and there's also a condition that a star must have existed originally with the star grid, and that also is a boolean. And after this start, then we have to add all values would be false if there's no stars that are there, right? And then we have to add another for loop for handling the black pixels, and two loops that visit every cell will basically, which will have like a row number and a column number, and they'll just like, visit every single cell of the picture. And so just basically go through the entire grid so we don't miss any of the black pixels. And we want to obviously check, is the pixel black? So we have to add an if and final image, and we have our row and column, and if it equals the B, then we know that the pixel is black. And if not, then we can just, return -1. So we can have the black pixel means that it existed before and after, so the star must have moved from R minus B and C minus A, so we have to include that. And if it's outside the grid, as like I said, it's impossible, so we return -1. Now we have to force the stars to exist, right? So one at the black pixel and one where it came from. So we have our star grid row and column is true, and also our shifted star grid has to be true. And these stars are required but not optional. So now we have to handle the white and gray pixels, right? What this means is that we again have to scan the entire grid using the for loop and to check for contradictions and fill in gaps. So we have to do our for loop and for loop again to check for the rows and check for the columns like we did. And then we have to have our conditional with the final image, row and column. If it equals W, that means that there is a pixel that is white. And so what white means that there's no star ever. So if we already place a star here, then we'll have a contradiction. So the answer will be impossible, right? So if star grid row and column, then you return -1. So we also have to include an else if it's gray, right? We want to also check if it's gray. So that means the star exactly has one photo. And again, you have your conditional. And if the star already exists here, then this gray pixel needs to be explained and you have to move on, right? So you have to have continue. Now, you have to check if a star could have moved into this spot. And if so, the gray pixel has been explained and you would move on. So you'll have your if, and if R is greater than or equal to B, and if C is greater than or equal to A, and if the star grid R minus B, C minus A, if that's true, then you just continue. So you know that the greatest pixel has been explained. And if nothing explains this greatest pixel, we must place a star here, right? That's our definition. You can go back and rewatch where I explained the problem to understand that, right? So our star grid, row and column, we have to set it equal to true, and this will increase the star count, but it is necessary, right? Now we have to count the stars, right? This is the main part of the problem. So we have to create a counter, right? We can just call it int answer, set it equal to 0. We do our loop, go through the whole entire star grid just one more time, and then if a star exists at that position, we add 1 to our answer. So this is pretty self-explanatory, and then we just return it. So now that we've done that, so now we have the code for actually finding out how many stars we need and the minimum amount that we need for photo 1. So now we have our main, and this is where the program will basically start running. And you want to add the input/output to be faster, and you use the iOS sync with Studio and set it equal to false, and sin.tie the null PTR. You want to go and watch a video. There's a bunch of videos that explain why you have to use these things, but we'll probably explain it in a later video. And then what you have to do is read how many test cases there are. So you have to have it in, and we'll just call it T, and then you obviously want to have your sin, right? And while T is minus minus, we want to solve the case. So run the solve case once per test case, and then print the answer each time. So that's what this part is doing. So it's printing it out, and then we're running it once per test case. So we're using a while loop. And then we just return 0. And what this means is that the program has ended successfully. So, all in all, this is definitely one of the tougher problems that we've done. And so, I do hope you enjoyed. If you have any questions, you can always email us. And I hope you have a great day, and take care.